Hello everyone, my name is Nick West. I'm the course coordinator for molecular microbiology, or MICR3003. This course, we began a new practical last year which was introduced, and it was planned before the COVID-19 outbreak, but it's called Outbreak Response. And it's designed to illustrate how we can deal with such events, even on a shoestring budget. What we're designing here is responding to a localized epidemic, and how we can use and harness molecular microbiology of a very modern format in order to enable us to identify pathogen, develop vaccines, and quickly respond to these outbreaks which do occur sporadically throughout the globe. It's sometimes quite easy to develop diagnostics of a high-tech solution. If we were working in a building like this, that's no problem at all. We're able to harness all of the technique, the expertise, the electricity, and our expensive equipment. But imagine if you were placed in a remote environment where we don't even have electricity. How do we go about diagnosis? How do we go about solving the problem and bringing vaccines to those people in a rapid fashion? Now, we're only able to do that because our techniques have developed so far that they're of a high level of an advanced molecular nature. It's challenging, but we can do it, and that's what we're going to do in MICR3003 Practical 1 Outbreak Response. So the scenario is, as I mentioned before, is you've been sent with your lab partner into a remote location like this one here, where we don't have the luxury of electricity. And all you have is your backpack and your fundamental molecular biology tools. And with that, you're going to diagnose the problem. What is the infection that is causing the outbreak? And we'll go on from there and describes with you how you're going to solve that issue. You're going to use techniques in this practical that have not been seen by the vast majority of undergraduate students. Indeed, most people in advanced research laboratories aren't even using such techniques. The first one you're going to look at is something called RPA. Now, if you know anything about PCR, you'll understand that it is amplification nucleic acid, right? But that requires expensive thermal cycling and a lot of training. Right? RPA is different. RPA is what we're going to use as our isothermal amplification technique to amplify nucleic acid without electricity. We don't require high levels of training for this either. But it's what's happening inside the tube that you'll see, which is quite astounding. We call this a point of care diagnostic, meaning that we can go to where the problem is to diagnose the issue. We don't need a laboratory setup for that, and we can do it indeed in this wilderness that we found ourselves. Second thing we need to do is, once we've amplified this nucleic acid, we could say whether a pathogen is present or not based on the presence of this DNA. Is how do we know that? How do we see that? And normally you'd put that onto an agarose gel. We'd run it out and we'd electrophoresis it and stain it and look with, again, some highly sophisticated instruments. We need to develop a system by which we know if it's positive or negative simply by looking at it. And we call that naked eye detection. And we'll run through that as well. Then we're going to start to assemble our vaccine construct. We've identified the pathogen. We're going to try to understand now and try to develop the antigens that we're going to make for our vaccine. And that involves cloning. And some of you may have been involved before in typical ligase-dependent cloning. Well, we've developed a technique here at UQ within my lab called homologous alignment cloning, or HAC. And it doesn't require the use of these enzymes. And it's an extremely rapid and very cost-effective method that you're going to learn in this course. We're also going to make our own competent cells. We're going to begin the cloning within these competent sites that you've made. Homegrown transformations, again, simply and efficiently. We'll then identify the antigens which are going to make the best vaccine candidates. We'll screen patient sera, get some samples from patients and detect whether or not our chosen antigens are in fact immunogenic and therefore stand a chance of being the next vaccine. Now let's go inside and I'll explain this in more detail.